Alright, so this is my next exemplar for modern physics, and it's asking me to derive the energy for a hydrogen atom, and specifically Bohr's model. So in Bohr's model, the main ideas are that energy is quantized. So what that means is that when a photon comes in and hits a electron, that's a specific amount of energy. It's like a packet. And then the levels of energy will match. So the energy hitting the electron will be the same amount of energy when this electron pops up to the next excited state. The potential energy that it now has is the same amount of energy as the photon that hit it, and vice versa. So if this electron goes down a state of energy, so it drops down an excited state, it will release a photon, and that photon will be the same amount of energy that it dropped. To derive energy, we want to conceptually understand where the forces are coming from. So there's a proton, hydrogen's one proton, and it's attracted to its one electron. Now, there's two forces. There's the electrostatic force, or the electric force, and then this is the force that the proton is attracted to the electron due to opposite charges. And then there's also force, centripetal force of the electron, because it's traveling in a circle. And then the force on the another force on the electron is, I guess it's not necessarily a force, but it has a velocity vector. Now, the electric force, you'll learn this in E&M. You have coulombs, it's equal to Coulomb's constant times Q1 times Q2 over the radius between the charges. And then the centripetal force is equal to, well, we have force is equal to ma, and then there's acceleration. Centripetal acceleration is the velocity squared over the radius. So if we input this into the F equals ma equation, you get m times velocity squared over r. Now, the electric force and the centripetal force are equal in magnitude, and they're opposite in direction. So you can set them equal to each other. So the electric force is this, and the centripetal force is this. Now we can cancel R's. And then also, the proton and electron have the same charge. So Q1 and Q2 are equal to each other. So we can just say they're the same variable. So if we simplify a little bit, we can just use E for their charge. And then it's squared because there's two of them. There's just an R here and mv squared. Now notice that what we want is energy is equal to kinetic energy plus its potential energy. Now, already, after just diagramming and writing down some equations, I noticed that mv squared is very close to the equation for kinetic energy. The equation for kinetic energy is 1/2 mv squared. So if we multiply both sides by 1/2, now we have what kinetic energy is equal to. So the kinetic energy of the electron the kinetic energy of that is 1/2 Coulomb's constant E squared over R. Now, the next step also comes from electromagnetism. Remember, the total energy of the system is equal to its kinetic energy plus its potential energy. So now we have kinetic energy, we want potential energy. So the potential energy of particles or charges is equal to Coulomb's constant Q1, Q2 over R. Now, when two charges are, okay, so first let's start by simplifying again. So the potential energy is equal to negative K E squared over R. The Q, both Q's, again, the charge of a proton and electron are the same, so they can be the same variable. And then you must be wondering where this negative comes from. Now, when two charges are infinitely apart from each other, if they're infinitely far from each other, we say that the potential energy is equal to 0. Now, as they get closer to each other, as this dot gets closer, so let's say it's here now, we say that potential energy decreases. So the potential energy will be lower as the two charges get closer. The negative sign indicates this phenomenon. So that's why that negative sign goes there. Next, now that we have potential energy and kinetic energy, all we do is we plug into this equation. So the total energy of the system is equal to its potential energy plus, it's potential plus its kinetic. So here we have a positive 1/2 and a negative 1 of the same thing. So 1/2 minus 1 is equal to negative 1/2. So the total energy is equal to negative 1/2 just like that. There should be an R here. And there should be no 2 here. There we go. So negative 1 plus 1/2 is equal to negative 1/2. And then there's a square here too. Now, this is an equation that we can use to find the total energy. Coulomb's constant. We know the charge of protons and electrons, and we know the radius of this electron depending on its state. So, for example, the radius of an electron, of a hydrogen electron at ground state is equal to 5.3 times 10 to the negative 11. And then that's over k times e squared. And the Coulomb constant, k, is equal to 9 times 10 to the 9. And the charge of a proton or an electron, doesn't matter which one, is equal to 1.6 times 10 to the negative 19. We multiply that by 1/2, because that's the equation, and there's a negative. So, when you calculate the ground state, the energy of a hydrogen atom at ground state, this equals 13.6, and these are electron volts, and it's negative. Now, to calculate the energy for other states, because this is in ground state, you would just find the radius of the electron, because as the electron increases excited states, it has a larger radius, and you would just input that radius into the equation. So, as the excited state increases, the radius will increase, and you can input that radius here, and then the energy will be equal. However, we can make this equation a little bit more clean, because what Bohr was asking was, he was expecting for the spectrum of the hydrogen atom to be continuous. However, there's distinct emission lines. So he came up with the idea that momenta, radii, and energies are quantized by whole numbers. And so this radius r n, and depending on what state it is in, he said this is equal to the quantum number squared times the ground state radius. So we can call that R1. So if we just plug that in, so now this is more of a general equation. The energy for the nth state, excited state, is equal to negative 1/2 ke squared over Rn So then we can plug in Rn, and we get that. Now, what we can do next is factor out n squared. So we'll get En is equal to negative 1/2 ke squared over R1 times what we're factoring out, so 1 over n squared. Now what that does is, all of these are constants. Sorry, all of these are constants here. So we can find the value for this no matter what excited state it's in. And we calculated that in the ground state. So En is equal to negative 13.6 electron volts times 1/2 over n squared. And that's the energy equation for the hydrogen atom. So